Why, when you charge your phone, your charger heats up? This is electric power. And there's one clean formula that explains heat, light, and danger. So if you think back to work and energy, the key idea of power is energy per time. It's the rate at which energy is transformed. And in electricity, if a charge, Q, which is represented in coulombs, moves through a potential difference, which is V, volts, the energy transferred would be charge multiplied by volt. So now power becomes QV over time. And charge per second is also known as current. So power is also equal to IV, where power measured in watts is equal to current, which is amps, and voltage V. This might remind you of something, of Ohm's law. So I'll give you two variants of this equation. Using Ohm's law of V equals IR and our new power equation we just found, if you sub in this value for V, here P equals I squared times R as the first variant. And if you rearrange Ohm's law, you get current equals voltage over resistance. So we can sub in this value for I into the original Ohm's law to get P equals voltage squared over resistance. These are your three power formulas, and you choose one depending on what you know. It lets you calculate the power dissipated by a resistor. Here's a real-life analogy. Electrons moving through metal moves like runners pushing through a crowd. Every time they bump into an atom, they lose a bit of energy, and this energy turns into heat. This is how wires, filament, and heating elements glow. You're watching electron collisions turn into light and fire. Example problem. The problem is, how do you calculate the resistance of a car headlight drawing 40 watts from a 12-volt battery? Why? Because knowing the resistance lets us understand how the bulb reacts to current and why it might burn out. Here's what we're given. Watts is power, so 40 watts of power. V is voltage. And what formula links up resistance, power, and voltage? If you download the free cheat sheet in the description, which has all of these formulas, the one that links up all three is one that we just looked at. P equals V squared over R. And we can rearrange for R with our fast math to get R equals V2 over P. And if we plug in our values, so voltage being 12, power being 40, then our answer for resistance is 3.6 ohms. This is while the bulb is on and drawing power. But when it's cold, the resistance will be lower, which is what I talked about in the last video. Which is why bulbs often burn out the moment they turn on, because there's a huge surge of current. Here's a slightly different example problem. Here's the setup. Your heater is on for 3 hours a day. The current going through your heater is 15 amps. The voltage is 120, and it costs 9.2 cents per kilowatt hour, which means that the amount of energy used with a power of 1 kilowatt every hour, it's cost 9.2 cents. We're looking for the monthly cost of this energy. How do we do this? How long we're actually using the heater per month. 3 hours a day multiplied by 30 days in a month gives us 90 hours per month. Now let's calculate power so that we can find the amount of kilowatts we're using. And then we just have to multiply it by the amount of hours we're using it for. What are we given and what formula links up with power? We're given current, we're given voltage, given time. There's a formula that links up power with voltage and current. P equals IV. Get the cheat sheet. We can plug in our values for current, which is 15, and the voltage is 120. Gives us 1,800 watts, and in kilowatts it's 1.8. How much energy is actually being used every month? Let's multiply the kilowatts of energy by the amount of hours we're using it for, which is 162 kilowatts per hours. Now, how about how much it costs? It's 9.2 cents for every kilowatt hour. So we simply multiply them. And in dollars, it's $0.92, giving us $15. So your heater every single month costs $15. Time for a third example, and it's about lightning. And this lightning bolt transfers 10 to the power of 9 joules in a 0.2 second time interval across 5 times 10 to the power of 7 voltage. And we're looking for the power. Let's look at this backwards. Power is energy divided by time. Energy, 10 to the power of 9 joules. Time, 0.2 seconds, giving us 5 times 10 to the power of 9 watts, which is 5 gigawatts, or GW. This is 5 billion watts of power in one single lightning strike, which is an insane amount of energy transfer per second. But what if we want to know the total charge transferred? The energy transferred by electric charge depends on how much charge Q moves through how much voltage V. So energy is Q times V. We can rearrange for Q, giving us Q equals energy divided by voltage, which is 10 to the power of 9 over 5 times 10^7, giving us 20 coulombs of charge moving from the cloud into the ground. What if we want to know the current? Current, which is I, is defined as the rate of charge flow. So how much charge passes through every second? Q per time. 20 coulombs is the charge that we just found. The time is 0.2 seconds, which is 100 amps. This means during the flash of lightning, it carried 100 amps of current. How about power in household circuits? The problem is overheating, because all house wires have some kind of resistance. So when a large current flows through, power becomes dissipated, because P equals I squared over R equation. More current equals more heat. And if too much heat builds up, insulation will melt, which is a fire risk. So here's some real-life safety systems. So there's something called fuses. And fuses are one-time safety wires that melt when the current exceeds a limit. And there's also circuit breakers. Circuit breakers are switches that flip open when the current is too high, and it can be reset. For example, if the current is over 20 amps, then the breaker will flip. Let's go through an example on this topic. The goal is to check whether or not a 20 amp breaker will trip when multiple devices are used at once. Let's say we have a 120 voltage outlet, like this. And plugged into this outlet, we have a desk lamp with 100 watts of power. We have a heater with 1,800 watts of power. We have an amplifier, which is 175 watts, and a hairdryer, which is 1,500 watts. We're seeing if this is going to trip our breaker when the threshold is 20 amps. Let's add up all of these powers in terms of current, because amps is in current. The formula we use is rearranged from the power formula, which is on the cheat sheet in the description. It's I equals P over V. And if you apply this to each of these values, you find for the desk lamp, it's 0.83 watts amps plus the heater, which is 15 amps, plus your amplifier, which is 1.46, plus your hairdryer, which is 12.5. In total, your current is 29.79 amps. So yes, the breaker will trip. This is why high-power devices will need their own circuit. Here's a quick conceptual example. Why can your cord catch fire? If your heater is drawing 15 amps of current through this wire, and let's say the cord is very thin and this overheats it, the cord cannot handle 15 amps. It melts the insulation, which is a fire hazard. So it's not just about watts and power. It's about how much current your wire can actually handle. Here's a quick recap. P equals IV gives you the total power used. P equals I to R tells you how much heat is generated, and overloads can start fire.